So you are muted.
So the question that I have written is, arrange the following in increasing order of bond length. O2, O2 plus, O2 minus, O2 2 plus, O2 2 minus. So on the basis of molecular orbital theory, we are asked to arrange in increasing order of bond length. So how should we proceed with such type of question? So in order to solve this question, let me tell you that there is no direct way of calculating the bond length with the help of molecular orbital theory, but what we can calculate is the bond order, and the relation between bond length and bond order is they are inversely proportional to each other, which means more the bond order, lesser will be the bond length. Now molecular orbital theory helps us to understand the helps us to calculate the bond order, and last class we have discussed the molecular orbital diagram for oxygen molecule. We need not draw the molecular orbital diagram for each and every molecule. That is not required. Okay, each and every molecule is not required. So I'll give you just a shortcut to carry out this particular process. Just focus on oxygen molecule and draw its 2p orbital diagram. Okay, 2p orbital diagram. Now remember, last class I had told you that the oxygen's diagram should be of this manner. The oxygen has how many electrons in the 2p? It has 4 electrons. 1, 2, 3 and 4. 1, 2, 3 and 4. So total of 8 electrons are to be distributed, and when you are to distribute 8 electrons, it's 1, 2, 3, 4, 5, 6, 7 and 8. So there are 2 unpaired electrons in the pi star 2px and pi star 2py. So on the basis of this energy diagram, we will be calculating the bond order of each and every one. And how to do it? Oxygen, half of bonding electrons are 6, anti-bonding are 2. So this is 2. Now one might ask me that why are we not considering 1s and 2s? Because even if we consider 1s and 2s, the bond order will still come out to be 2, because number of bonding and anti-bonding in oxygen molecule will nullify each other, will cancel each other, and whatever result comes out actually comes out on the basis of 2p. So when you are asked to draw the complete molecular orbital diagram of oxygen, you have to consider 1s and 2s also. But here we need not draw the complete diagram. Here just a comparison is to be made. Now come to O2 plus. Now what's the meaning of the term O2 plus? It means that you are removing 1 electron out of oxygen molecule. Where from the electron will be removed? The electron is always removed from the outermost orbital and added up also to the outermost orbital. And here the outermost molecular orbitals are these 2, which are anti-bonding. So if you are removing 1 electron, it will be removed from the anti-bonding. So there will be only 1 electron remaining, and this will come out to be 2.5. Then comes O2 plus, O2 minus. So in O2 minus, you are to add up 1 electron. And when you are adding up electron, it will go to anti-bonding again. So it will be half of 6 minus 3, which is 1.5. Then comes O2 2 plus. So when you are asked to write down the molecular orbital diagram for O2 2+, it means 2 electrons are to be removed. And where from they will be removed? Both the electrons will be removed from anti-bonding. So it will be 6 minus 0 divided by 2. That will come out to be 3. And O2 twice minus, where 2 electrons are to be added up to the anti-bonding. So O2 twice minus will come out to be half of 6 minus 4, that is 1. So these are the results that are obtained. If anyone has got any doubt, please inquire about it. See how we have done. Please ask me if you have got any doubt. Whose molecular orbital diagram is this?
Oxygen.
O2.
Oxygen.
And on the basis of this O2, we will be adding up electron or subtracting electron. When you are adding up electron, the addition will be going in the anti-bonding. When you are subtracting the electron, the subtraction is also going on from the anti-bonding. And depending upon what is the charge, how many electrons are to be added up and how many electrons are to be removed, accordingly, you have to put in or remove the electrons, and you get the bond order in this manner. But the question asked is not to arrange them in increasing bond order, but to arrange them in increasing bond length. And as I said at the very outset, that bond length and bond order are inversely proportional to each other. So if you are to arrange them in increasing order of bond length, who do you think will have the least bond length?
3.
3 means?
Sir, O2 2 plus.
O2 2 plus.
O2 2 plus. Followed by?
Sir, O2 plus.
O2 plus.
Followed by O2, followed by O2 minus, followed by O2 2 minus. So this is a very, very important question that is generally asked. Okay. So you'll have to remember the order, and how the order has come, that you must be aware of. Is the solution understood to everyone?
Yes, sir.
Okay. Write it down. Then we shall discuss one more of similar type. Shall I proceed?
Yes, sir.
Okay. So same way, if instead of taking oxygen, suppose the question asked is, arrange the following in increasing order of bond order. So directly bond order is to be arranged. Arrange the following in increasing order of bond order. N2, N2 plus, N2 minus, N2 2 plus, N2 2 minus. So how we are going to solve this one out? Let us try to understand. So whose molecular orbital diagram you will draw now as the basis?
Sir, N2.
N2. And N2's diagram is different than that of oxygen, because boron, carbon, nitrogen have a different diagram. So you have 2 pi orbitals below and sigma above. And for nitrogen, you have 3 electrons each. And when you put them in, this is the scenario. So for nitrogen molecule, it is half of 6 minus 0, that is equal to 3. Now I want all of you to calculate yourself and thereafter you tell me the results. Same procedure. Simply take care where you are adding up electron and where from you are removing the electron. So in case of nitrogen molecule, when you are removing the electron, you are actually removing it from bonding or anti-bonding?
Bonding.
Bonding. The lower ones are bonding, upper ones are anti-bonding. What have you got for N2 plus?
2.5.
2.5. All must get 2.5. Acha, N2 minus. When you are adding up electron, where are you adding up the electron, in the bonding or anti-bonding?
Anti-bonding.
Anti-bonding, because bonding is completely filled up. So here it is different from that of oxygen in the sense that when you are removing the electron, it is to be removed from bonding, and when you are adding up the electron, you are adding up to the anti-bonding. So take care of that fact and accordingly tell me what will be the results. Have you got it?
Yes, sir.
What is the result for N2 plus? Half of
5 minus 0.
5 minus 0, isn't it?
Yes, sir.
2.5. And what is the result for N2 minus? You are adding up electron here, so it will be 6 minus 1. This is also 2.5. Clear? Yes or no?
Yes, sir.
Yes, sir.
Because this will remain intact. The 6 electrons will remain intact, and you are adding up electron in anti-bonding, that will be subtracted. N2 plus, you will be removing 2 electrons from this. So it will be half of 4 minus 0, that will be 2. And in N2 minus, you N2 twice minus, you are adding up the 2 electrons in anti-bonding. So I think this will be also 2. Am I correct?
Yes, sir.
Okay. So here in this question, you are asked to arrange them in increasing order of bond order. The bond order will be lowest for these two. So how we are supposed to write? N2 2 plus is equal to N2 2 minus, less than N2 plus is equal to N2 minus, less than N2. So remember one thing, that bond order cannot exceed 3. Okay, in both the cases we have seen that beyond 3, if you add up electron, then also there is a decrease in bond order. If you subtract the electron, then also there is a decrease in the bond order. So in both cases, there is a decrease in the bond order. So maximum bond order possible can be 3 according to molecular orbital diagram.
Sir,
Yes.
can you explain it one more time?
See, nitrogen, I hope you have understood, half of 6 minus 0 is equal to 3.
Yes, sir.
Okay. Now, N2 plus means what? You are removing one electron. Where from the electron will be removed?
Bonding.
Bonding. So there will be 5 electrons left, isn't it?
Yes, sir.
So half of 5 minus 0 is 2.5 or not?
Yes, sir.
Okay. Now come to the next one, N2 minus. Now you are adding up electron. Where you are adding up electron?
Bonding.
How can it be bonding? Bonding is already filled up. Anti-bonding. So when you are adding up electron in anti-bonding, so will it not be 6 minus 1?
Yes, sir.
Is it clear?
Yes, sir.
Okay. So keeping in mind the nitrogen, we are adding and subtracting the electrons. So that is why we have kept nitrogen intact. And thereafter we have added up electron or subtracted electron depending upon what is the charge possessed by it. Understood?
Yes, sir.
Anyone having still doubt? Please tell me. No doubt. Have you written it down? Can I proceed?
Yes, sir.
Okay.
Yes, sir.
So these two must be remembered, one for oxygen and one for nitrogen. So oxygen and nitrogen molecules are most often asked. So after discussion of molecular orbital theory, these two questions were remaining because you might get questions of this sort, increasing order, decreasing order. So there you have to do the calculation and proceed. So after discussion of this, we now move on to the next very important topic, that is called dipole moment. Dipole moment, which is symbolized by this. So what exactly is dipole moment? So in order to understand the concept of dipole moment, we have to recall that there are two types of covalent bonds on the basis of polarity, one of which is called a non-polar bond and one of which is called a polar bond. So which is a non-polar bond? If the two atoms combining have similar electronegativity, then the shared pair of electrons will not be shifted to any of the direction, and thus none of the atoms will develop any partial charge on them, and therefore such kind of molecules are referred to as non-polar molecules. Okay. Similarly, if the bond is formed between two different atoms, out of which one is more electronegative, say B is more electronegative, then the shared pair of electron will not be lying exactly in between A and B. It will be rather slightly shifted towards B, giving B a partial negative charge and A a partial positive charge, and such a bond is referred to as polar bond. And the molecule becomes polar in nature. Now the question is, if you consider a diatomic molecule like that of H bond F, H bond Cl, H bond Br, H bond I. So all these molecules are polar in nature. And why are they polar in nature? Of course, because they all have polar bonds present in them. So if you have a polar bond present, then the molecule will be said to be polar, provided it is a diatomic molecule. So because in every case, the halogen atom is more electronegative, So the pull will be towards the halogen atom, and we show the pull with the help of this sign. This is the sign for dipole moment. Every molecule is polar and there is a pull towards the halogen atom. But the question arises, will the pull be same or will it be different? So of course, the atoms are different, so therefore the pull will be different, and fluorine is going to pull to the maximum extent because of the fact that fluorine is most electronegative out of all. So all of them are polar, but H bond F has maximum polarity. So this is decided on the basis of what is called as the dipole moment. So when it is asked that in what way the dipole moment is important to us, so remember, dipole moment helps us to measure the degree of polarity. How much polar a molecule is, that is decided on the basis of dipole moment. And mathematically, dipole moment is denoted as modulus of E into D, where modulus of E is defined as magnitude of charge developed on any of the atom. Say if in this particular case, A is developing del plus, B is developing del minus. So magnitude of any of the charge will be 1. Sometimes they may develop del 2 minus, del 2 plus. So in that case, the modulus of charge will be 2. And D is the distance between the two charges. Distance between the two opposite charges. So greater the magnitude of charge, more will be the dipole moment, and at the same time, more the distance between the opposite charges. It means that more is the pull of the electron cloud, due to which the distance increases. So more will be the dipole moment. So dipole moment helps us to measure how much polar a molecule is. If dipole moment comes out to be 0, then of course it will be a non-polar molecule. So for non-polar molecules, dipole moment is 0. And for polar molecules, it is a non-zero value. And greater the value of mu, more will be the dipole moment. And this is very simple as far as the diatomic molecules are concerned. Now coming to the units of dipole moment, what are the different units in which this mu is expressed in? This is charge, and charge has SI unit of coulomb, and this is distance. Distance has SI unit of meter. So SI unit for dipole moment is coulomb meter. Okay. CGS unit for charge is ESU, and the full form of ESU is electrostatic unit, and CGS unit for distance is centimeter. So accordingly, it will be product of the two, ESU centimeter. But apart from the SI unit and CGS unit, there is one more common unit which is used, and it is called Debye unit, DEBYE, as a mark of respect to that particular scientist who worked upon the concept of dipole moment. So what is the relation between Debye and the different units? So let us write it down. 1 Debye is denoted by capital D, is equal to nearly 3.33 into 10 to the power minus 30 coulomb meter. And in case of CGS unit, it is 1 into 10 to the power minus 18 ESU centimeter. So this is the relation between the most common unit, Debye, SI unit and CGS unit. So hence, you should be aware of the relation, because sometimes while doing the objective type questions, the relation may be asked. So far, whatever we have discussed in terms of diatomic molecules, molecules containing only 2 atoms. But what if a molecule is polyatomic? It means that the central atom is surrounded by more than 1 atom. So obviously it will be called as polyatomic. So in general, polyatomic molecules are those which contain more than 2 atoms and therefore more than 1 type of bond in it. So let us try to understand what happens in case of polyatomic molecules. I give the example of carbon dioxide molecule and water molecule. And we are familiar with the fact that from VSEPR theory, carbon dioxide is a linear molecule, whereas water has a bent structure, has inverted V shape. So at first, we will look out for each and every individual bond, whether they are polar or not. And not only that, the direction of the dipole moment will be towards which particular atom. Now tell me, if you consider carbon-oxygen bond on the left-hand side, who is more electronegative out of carbon and oxygen?
Oxygen.
Oxygen. So direction of the dipole moment will be towards oxygen. In this particular case, again, oxygen is more electronegative, so direction will be towards this. Now, dipole moment is a vector quantity, which means that it has both magnitude as well as direction. And we are going to apply all the characteristics of vectors in dipole moment that you have learnt in physics or mathematics. And we know that equal and opposite vectors always cancel each other. So ultimately, we see that in carbon dioxide molecule, due to its linear structure, the 2 bonds are arranged in such a way that the dipole moments arising out of these 2 bonds nullify each other, cancel each other. So what do you think will be the dipole moment of carbon dioxide? Yes, 0.
0.
Of course, it will be 0. So you see, in case of polyatomic molecules, simply having polar bonds is not enough. It is equally important to know that what is the direction of the polar bonds. If the 2 polar bonds are nullifying each other, then of course the net dipole moment will be 0. But in case of water, oxygen is more electronegative with respect to hydrogen. So it is going to have direction towards oxygen, and both of them are added up because both of them are moving towards oxygen. And because there is addition of vectors, it's not nullification or cancellation. So dipole moment of water will not be 0. And because it will not be 0, so we say that carbon dioxide is a non-polar molecule, whereas water is a polar molecule. Is it understood? Yes, is it clear or not? Tell me.
Sir, can you explain H2O again?
H2O. Okay. H2O is linear or bent?
When?
It is bent. How do I know that it is bent? Which particular theory helps us to understand the shapes of molecules? That has already been done previously. There was a very important theory with the help of which we could predict the shape of molecules. What was that theory?
Molecular orbital theory.
No, molecular orbital theory does not help us to predict the shape.
VSPR.
VSEPR theory, valence shell electron pair repulsion theory. So valence shell electron pair repulsion theory says that carbon dioxide has AB2 shape, whereas water has AB2L2 shape. It means that AB2L2 shape will be inverted V shape. So on the basis of VSEPR theory, we have drawn the inverted V shape. And here you will see that the two bond moments are not nullifying each other as they are moving towards the same direction. So if vectors are moving towards same direction, are they added up or are they subtracted from each other?
Added.
They are added up. So if the two dipole moments are added up, will the result be zero or non-zero?
Non-zero number.
Non-zero. So if it is non-zero, the molecule will be polar or not? Understood?
Yes, sir. Understood.
And if it is zero, then it is non-polar. So how do I
Non-polar.
know that which molecules in case of polyatomic molecules are non-polar in nature? So all those which have symmetrical shapes. What are the molecules which are symmetrical shapes according to VSEPR theory? AB2, linear. AB3, what was the shape of AB3? Tell me.
Trigonal planar.
Trigonal. What was the shape of AB4?
Tetrahedral.
Tetrahedral. What is the shape of AB5?
Trigonal bipyramidal.
Trigonal bipyramidal. What is the shape of AB6?
Square bipyramidal.
Octahedral.
Octahedral or square bipyramidal. And AB7 was pentagonal bipyramidal. So if a molecule, remember, has a central atom and is surrounded by same type of atoms and possess any one of these geometries, including AB7, which is pentagonal bipyramidal, then they are coming to or coming under the category of non-polar, because the bond moments or dipole moments arising out of these bonds will mutually cancel each other. But if a molecule is unsymmetrical, and when will the molecule be unsymmetrical? A molecule will be unsymmetrical when it has a lone pair of electrons along with the bonded pairs, or even if it has a symmetrical structure but the atoms in the surrounding are different, then in such case there will be a net dipole moment and such molecules will be referred to as polar. Understood or not?
Yes, sir.
See, when we talk about CCl4, it has exactly AB4 shape. So what do you think will be CCl4, polar or non-polar?
Non-polar.
It will be non-polar. Now, when I talk about CHCl3, this is also symmetrical, has tetrahedral shape, but in spite of having tetrahedral shape, the CHCl3 is not non-polar. It has some net dipole moment. Why do you think it has got a net dipole moment?
Chlorine
This
is
is
in
also
different direction.
tetrahedral. This is also tetrahedral. Why do you think it is non-polar? It is polar in nature.
Because it is not surrounded by similar.
Very good. Because it is not surrounded by same kind of atom. So two criteria are to be fulfilled. First of all, the molecule must be symmetrical. And secondly, the molecule must have same type of atom in the surrounding, because then only the magnitude of the dipole moments will be capable of nullifying each other, cancelling each other. Is it understood?
Yes, sir.
Yes, sir.
So hence, when you are given to predict whether the given molecule is polar or non-polar, so we are going to apply the same VSEPR theory at first to at least apply so as to predict the shape of the molecule. Once the shape is clear to us, say for example, we have two molecules, boron trifluoride and ammonia. So both of them look alike, but one of them is polar and the other is non-polar. So let us see which is polar and which is non-polar. Boron is 2, 3. So we will take 3 plus 3 into 7. That is 24 electrons, which makes out to be 12 pairs. So boron at the center, fluorine at the 3 corners. Complete the octet of the fluorine first. And while completing the octet, all the 12 pairs have been utilized, which means that the pattern of BF3 is AB3. And AB3 is trigonal shape. So trigonal shape is symmetrical. And because it is symmetrical, the dipole moments arising out of the 3 bonds, I'm showing the dipole moment towards fluorine because of the fact that fluorine is more electronegative. So the geometry is such that the 3 dipole moments mutually cancel each other. How they will mutually cancel each other? We can show it mathematically that if the 2 dipole moments, which are nothing but vectors, are inclined at an angle of theta, then the net dipole moment arising out of these 2 bonds will be downwards. And the magnitude of this one will be exactly equal to magnitude of this. You are familiar with the fact that if 2 vectors are inclined at an angle theta, the net resultant will be square root of vector 1 square plus vector 2 square plus twice of vector 1 into vector 2 into cos theta, isn't it? Have you got this formula?
Yes, sir.
Yes, sir.
Okay. So exactly in the similar way, this is vector 1, this is vector 2. The magnitude of the two, because the bond angle is 120 degree, it will be same as that of this. So accordingly, they will be nullifying each other. Come to ammonia now. Ammonia has nitrogen with 5 valence electrons, hydrogen with 1 valence electron each. So 8 electrons will be 4 pairs. So nitrogen surrounded with 3 hydrogen, but hydrogen, as you know, can only complete the duplet. So the 4th pair will go to the nitrogen, and this is AB3L and has a pyramidal shape. So is pyramidal shape symmetrical or unsymmetrical?
Unsymmetrical.
Of course, it is unsymmetrical. And if you look at the shape of ammonia, it has 1 lone pair and 3 bond pairs. And nitrogen, being more electronegative, will pull the electron cloud towards it from all the 3 directions. And because there is a pull from all the 3 directions, the net will be upwards. It means that there is some net pull, net upward pull, which will make mu of BF3 0 and mu of NH3 non-zero. Which out of the two is polar and which one is non-polar?
So the first one, PF3 is non-polar and the NH3
Yes, the
is
first one is non-polar. There is no net dipole moment. If mu is 0, it is non-polar. And the second one has a net dipole moment. So mu will be not equal to 0. And therefore it is polar. Is it understood now?
Yes.
So you have to take the help of VSEPR theory in order to understand the concept of dipole moment. Okay, so without VSEPR theory, if you are not aware of the shape of the molecule, whether it is symmetrical or unsymmetrical, then it will not be easy for us to complete or predict whether the given molecule is polar or non-polar in nature. So after explanation of the dipole moment, you can write the definition of dipole moment. It is the measure of degree of polarity and is defined as the product of the magnitude of the charge and distance between the centers of positive and negative charge. It is represented by mu. It's a Greek letter called mu. The pronunciation is mu, mu. So mu is equal to magnitude of charge into distance, which I have already discussed. It is usually expressed in the unit of debye its SI unit is coulomb. Coulomb, I have written it wrongly. COU, coulomb meter, and CGS unit is ESU centimeter. What is the full form of ESU?
Electrostatic unit.
ESU means electrostatic unit. And relation I have already given you. 1 debye equals 3.33 into 10 to the power minus 30 coulomb meter equals 10 to the power minus 18 ESU centimeter. Done? Can I proceed? Yes or no?
Yes, sir.
Okay. So this is as far as the definition of dipole moment is concerned. Then you continue with the dipole moment, right? Characteristics. Characteristics of dipole moment. Characteristic means the properties of dipole moment. It is a vector quantity and hence has both magnitude as well as direction. So it is a vector quantity and hence has both magnitude as well as direction, and that direction is always towards more electronegative atom. It is denoted by an arrow with a tail facing towards more electronegative atom. Facing towards more electronegative atom. Point number 2. Two dipole moments mu1 and mu2 when inclined at an angle theta the resultant dipole moment mu r is calculated using the relation mu r is equal to square root of mu1 square plus mu2 square plus twice mu1 mu2 cos theta. So say, for example, if two dipole moments of equal magnitude are inclined at an angle of 180 degree, which means that they are equal and opposite. Why do we cancel them? Because if I put cos theta as cos 180, which is -1, you will see that overall value will come out to be 0 because mu1 and mu2 are equal. Okay, so it will be mutually cancelling each other. So this way, all those symmetrical structures, whatever we have discussed, their geometry is such that the net dipole moment ultimately gets nullified. Point number 3. In case of diatomic molecules, so in diatomic molecules, there is only one vector because there is only one bond. The dipole moment is equal to the dipole moment of the bond. There is only one bond, and if that bond has some polarity, whatever dipole moment it will have, the molecule will have overall polarity of overall dipole moment of that value only, because here the question of addition and subtraction does not arise. The degree of polarity in such molecules, the degree of polarity in such molecules depends upon the difference of electronegativity between the two atoms. Okay, so in case of diatomic molecules, how much polar a molecule will be depends upon the difference of electronegativity between the two combining atoms. And that is what I discussed. Mu of H bond F will be greater than mu of H bond Cl, will be greater than mu of H bond Br, will be greater than mu of H bond I. Why is it so? Because fluorine is most electronegative. So accordingly, the difference of electronegativity will be highest in HF and lowest in HI, because H is common in all of them. So more the electronegativity of the halogen, greater will be the difference of electronegativity. Can I rub point number 1 and point number 2?
Yes, sir.
So now we talk about polyatomic molecules, which I have already explained, that in case of polyatomic molecules, not only it is important to know whether the bonds are polar or not, but it is equally important to know what is their spatial arrangement. And what is the meaning of the term spatial arrangement in space, how the different atoms are arranged. In polyatomic molecules, the dipole moment not only depends upon dipole moments of individual bonds, but also upon the spatial arrangement. If anyone is not clear about what is spatial arrangement, the term spatial has come from space. Space means 3 dimension, but also upon the spatial arrangement of various bonds in the molecule. Symmetrical molecules containing only one type of atom in the surroundings have net dipole moment of 0. And because the net dipole moment is 0, hence they are non-polar. So all symmetrical molecules, according to VSEPR theory, whether they are linear, trigonal, tetrahedral, as for example, carbon dioxide linear, BF3 trigonal, carbon tetrachloride tetrahedral, PCl5 trigonal bipyramidal, SF6 square bipyramidal. So as you can see that in every example, they are surrounded by only one type of atom, plus they are symmetrical, are non-polar molecules. So in spite of the fact that they do contain polar bonds in them, but in spite of the fact that they do contain polar bonds in them, the net dipole moment will come out to be 0. Unsymmetrical molecules have net dipole moment and hence polar. So these are the important characteristics of dipole moment which you should be aware of. So if you are given set of molecules and you are asked to find out that which one is polar and which one is non-polar, you simply apply the VSEPR theory, find out its pattern. If it is symmetrical and it consists of same type of atoms, then it is non-polar. Otherwise, it will be polar. So that will be the simplest thing to do to predict whether the given molecule is polar or non-polar. Is it understood? Clear? Are all the points clear or not? Or you have got any doubt regarding any point? Yes? Can I proceed further?
Yes, sir.
Yes, sir.
Okay. So this was all about dipole moment. Now we move on to the last topic of the chapter, that is hydrogen bond. So at first I'll explain and thereafter I'll write down the things. Hydrogen bond, which in short is also referred to as H bond. So how do you define H bond? As the name implies, in order to have hydrogen bond, first of all, the molecule must contain hydrogen in it. That is criteria number 1. And criteria number 2 is that hydrogen atom must be bonded to highly electronegative atom. Suppose we have a molecule H bond X. And of course, in the neighborhood, there will be similar type of molecules, H bond X all through. Now we know that X, if it is highly electronegative, then due to the difference of electronegativity, it is going to develop del minus charge and the hydrogen is going to develop del plus charge. Likewise, every molecule will have polarity on them. Now, interestingly, the bonds that I have shown here, they all are covalent bonds. Okay, so they are not hydrogen bonds. But if you look at this hydrogen and this halogen, or any electronegative atom, so they will develop an interaction between themselves, which is shown by 3 broken lines. So this type of bond is referred to as hydrogen bond. Okay, so they are hydrogen bonds. So hydrogen bond is not a chemical bond. Then what it is? It is an intermolecular force of attraction, which develops between hydrogen atom of one molecule and highly electronegative atom of another molecule in the neighborhood. And this particular hydrogen bond individually has a very weak magnitude, but because in a sample there will be innumerous number of such bonds present. So as it is said that individually, even if we are weak, but when we are forming groups, so groups of even weak people becomes very strong. So as a whole, the hydrogen bond is going to affect large change in the physical properties of the molecule, because it is the hydrogen bond which ultimately is responsible in uniting the molecules together. So as I said that one of the atom must be hydrogen, otherwise we would not have used the term hydrogen bond. The second atom bonded to hydrogen atom must fulfill 2 criteria. What are the criteria? Criteria number 1, the atom bonded to hydrogen must be highly electronegative. Highly electronegative means it should have very high power of attracting the shared pair of electron towards it, because then only it can make the hydrogens del plus. And number 2, the atom must be small in size. Must be small in size. So not only it should be highly electronegative, but it should be smaller in size. Now, according to the periodic table and Pauling's electronegativity scale, that we discussed during the periodic properties, the most electronegative atom is fluorine, whose value has been given as 4.0, followed by oxygen 3.5, followed by nitrogen and chlorine 3.0. So they are the most electronegative atoms in the whole periodic table. But will all the 4 fit into both the criteria? Answer is no. Who will fit into the criteria? Fluorine, of course, will fit into the criteria. Oxygen will fit into the criteria. Nitrogen will fit into the criteria, but chlorine does not. Then the question arises, why? Nitrogen and chlorine both have same electronegativity. But the question is, there are 2 points to be taken care of. That the atom must be highly electronegative, plus the atom must be small in size. So fluorine has electronic configuration of 2,7. Oxygen has 2,6. Nitrogen has 2,5, but chlorine is 2,8,7. So as you can see, chlorine has 3 shells in it, making it much larger. And that is why chlorine, when bonded to hydrogen, will be unable to show H bonding. And generally, when we talk about the hydrogen bond, the other atom must be either fluorine, oxygen, or nitrogen. Chlorine does not fit into this criteria. Why? Because it is not capable of fulfilling the second criteria due to its larger size. So due to hydrogen bonding, molecules come closer to each other, which will result in increase in boiling point, melting point, and solubility in water. So hydrogen bonding is a very, very important criteria. It's the strongest of all the intermolecular forces of attraction. So let us try to now define what exactly is hydrogen bond. Hydrogen bonding or definition to keep. The attractive force which binds hydrogen atom of one molecule with highly electronegative atom. What are they? Fluorine, oxygen, and nitrogen. None other than these three are allowed of same or other molecule is called hydrogen bond. As for example, suppose we have hydrogen fluoride. So first we will provide del plus and del minus charges on all of them. They all are covalent molecules, but due to the hydrogen bonding, there will be interaction developed and it will be continued from both the sides. So here, as you can see, the hydrogen atom is acting as a bridge between the two fluorine atoms. With one of the fluorine atom, it is covalently bonded, and with another fluorine atom, it is bonded through weak hydrogen bond. So if you are to compare the strength of these two bonds, of course, covalent bond is much more stronger as compared to hydrogen bond. But as I said, that individually hydrogen bond may be weak, but there will be so many such kind of bonds, and ultimately it plays a very important role. Let us consider the molecule of water. So these are molecules of water which are present in this manner. So I have drawn 4 molecules of water and the solid lines that I have drawn are not hydrogen bonds, they are covalent bonds. Oxygen is more electronegative than hydrogen. The oxygen will develop del double minus, because the two hydrogens will be del plus each. So far, I have not shown the H bonding, but when the molecules are closer to each other, the hydrogen atom of one water molecule will try to interact with oxygen atom of another, thereby showing H bonding in water. So if it is asked that what is the reason behind the hydrogen bonding, so it is due to the partial charges developed on the hydrogen atom and the highly electronegative atom bonded to it. And these partial charges are capable enough to attract the opposite charge in the neighborhood. Have you drawn both of them? Can I rub?
Yes, sir.
Yes, sir.
So now I use the term with highly electronegative atom of same or other molecule. And both the examples that I have given are different molecules. And when such kind of hydrogen bonding occurs, this is one molecule, this is altogether a different molecule, this is third molecule. So interaction between two different molecules will result in the type of hydrogen bonding called intermolecular hydrogen bonding. Intermolecular H bonding. So both the examples that I have given for HF and water are examples of intermolecular H bonding. So what is the meaning of intermolecular H bonding? When the interaction is between two different molecules. Nature may be same or different, but the molecules must be different. So all these molecules are different. So that is called intermolecular H bonding. So this intermolecular H bonding is more important than the other type of H bonding that I'll discuss now. And why it is important? Because it associates the molecule. It brings the molecules closer to each other. And this will ultimately result in the formation of increase in boiling point, increase in melting point, increase in solubility in water. So all these characteristics are shown in this type of hydrogen bonding, which is referred to as intermolecular H bonding. So what is intermolecular H bonding? It is a type of hydrogen bonding which develops between two different molecules of same or different type. Okay. What is the second type of H bonding? There are two types of H bonding, one of which we have already discussed. It is called intermolecular H bonding. The second type of H bonding occurs in very large molecules. So you will be able to understand only when I give the example of the second type. The second type of H bonding is called intramolecular H bonding. Intramolecular. What is the meaning of the term intra? Intra means within, and inter means outside. When there is inter-school competition, it means that the competition is between two different schools. And when it is intra-school competition, it means that the competition is within the same school. The students of the same school compete. So this is intramolecular H bonding. Say we have a large molecule of benzene which has OH group and a nitro group. This is a coordinate covalent bond which we have discussed during the initial phases of this chapter. So as a whole, it is a single molecule. The name of this molecule is orthonitrophenol. So when you do the nomenclature of organic compounds, you will learn that if two groups are adjacent to each other, they are given the name orthonitrophenol. Now what happens in this orthonitrophenol? You see that oxygen is bonded to hydrogen. So this is del minus, this is del plus. Oxygen is bonded to nitrogen. So here oxygen is more electronegative. So as a result of which, because the two groups are very close to each other, there will be interaction developed between the hydrogen atom and oxygen atom, both belonging to the same molecule. And that is why it is an example of intramolecular H bond. Now, intramolecular H bond is not associating different molecules because it is a single molecule. Rather, what does it do is it is resulting in cyclization or ring formation. So intramolecular H bond results in cyclization or ring formation within the molecule. And because it is not associating the molecule, so there is no change in the boiling point or melting point or solubility, or rather there is a decrease in the boiling point, melting point and solubility. So in short, we can say that intermolecular H bond is stronger than intramolecular H bond. Why? Because in intra, whatever power was there to form the hydrogen bond has been utilized within the molecule. But in inter, the power is utilized to join different molecules together. And when you are joining different molecules together and you need to depart them, you need extra amount of energy to again make them to go away from each other. That ultimately results in increase of boiling point, melting point, etc. So hence we can say that first of all, hydrogen bond is an intermolecular force of attraction that develops between hydrogen atom of one molecule with highly electronegative atom of same or other molecule. If it is same molecule, it is intra. If different molecule, it is inter. But generally, when it is not mentioned and it is simply said H bond, so we refer to inter. It is the intermolecular H bond, which is the stronger form of hydrogen bonding. So hence we can say that categorization of hydrogen bonding has been done into two types. One is inter and what is intra. Can you tell me why nitrogen and chlorine, though possess both electronegativity, chlorine is not capable of forming hydrogen bond? Why do you think?
because of its size.
Because of its larger size. So in order to show hydrogen bonding, two criteria must be satisfied. Number one, the atom should be highly electronegative, and number two, the atom should be small in size. And these two criteria are fulfilled only by three atoms, fluorine, oxygen, and nitrogen. And that is why in all the molecules where hydrogen is directly bonded to oxygen or fluorine or nitrogen, you will observe the concept of H bond. Clear?
Yes.
Okay. So this brings to the end of the chemical bonding chapter. It was quite a large chapter. The next class will get into the organic chemistry. Okay. Thank you. Good night, all of you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.